Definitions and terminology. Module 3, Centroid, Center of Gravity and Moment of Inertia. This is Dr. D. Govardhan, Professor Emeritus, Department of Aeronautical Engineering, Ministry of Aeronautical Engineering, Hyderabad. Center of Gravity. Center of gravity of a body is the point through which the entire weight of the object assumed to be passing through it or acting through it. A body is having only one center of gravity for all positions of the body. Generally, it is represented by CG or simply G position. The center of gravity, it is always related to the three-dimensional object. That means which is having volume as well as the weight. Centroid. The word centroid, it is representing center of gravity of the plane areas as well as the unidirectional objects. The centroid, it is the point at which the entire area of the plane assumed to be concentrated, irrespective of its orientations. It is again represented by CG or G position. The center of mass. Center of mass is a point at which the entire mass of the object is assumed to be concentrated. The point remains constant for all the position of the bodies. It will not change the position of the body now. The body is always having only one mass center. The center of mass and center of gravity both are related to the three-dimensional objects and assumed to be same if the gravitational field is uniform. The difference between the center of gravity and centroid. Center of gravity, always it is related to the bodies which is having volume as well as the weight. But the centroid, that word implies for the lines as well as the plane areas and sometimes for the volumes also. The center of gravity is the point through which the resultant gravitational force of a body assumed to be passing through it and it remains constant for all orientation of the body. The volume such that the moment of area about any axis through the volume of such that the moment area of about any axis through the point is 0. Axis reference. In order to represent the position of the center of gravity or the centroid, some reference position is required now. Because without knowing the position of reference lines, it is difficult to locate the position of the centroid because the distance is required with respect to certain axis now. That axis is known as reference axis. The reference axis generally it is taken as horizontal line which is passing through the lowest point of the given object or the figure now. And the vertical reference line is taken as the line which is perpendicular to the horizontal axis and passing through the left hand side of the given figure or the object now. Here these two axes, horizontal axis as well as the vertical axis, generally is represented as the x-axis and y-axis respectively. Both are perpendicular to each other. But sometimes If the object is symmetrical now, maybe with respect to the vertical axis or horizontal axis, sometimes it may be symmetrical for both the horizontal and the vertical axis. Example I am taking here now. The object is now it is in the form of rectangle. It is there. Here, this object is symmetrical about the vertical axis as well as the horizontal axis. Hence, the intersection point is treated as the origin, and the x-axis and the y-axis we can take it down. In this case, when the object is symmetrical about the vertical axis and the horizontal axis, the intersection of vertical axis and the horizontal axis is treated as a position of centroid or center of gravity. Similarly, the object is said to be symmetrical about the vertical lines. The best example is it is in the form of here T section. It is there. Here in this case, the symmetrical vertical line is treated as a y-axis. The horizontal line, which is passing through the lowest point of the T section, is treated as a x-axis now. So the position of the reference lines that are most important. When we are selecting proper reference lines, the calculations which is involving in determination of center of gravity, it become simple. The methods of for determination of center of gravity. Generally here, three methods are applicable for determination of center of gravity or centroid of the objects. They are geometrical constructions. The second one is by method of movements. The third one is graphical method. Here, according to the geometrical consideration, here the object is, these are called the simple objects now. They are rectangle, triangle, circle, semicircle, quarter circle, and ellipse. Okay, for these objects, the area of rectangle is given by the product of width and height BH. For triangle, half into BH. For circle, pi r square. Okay, in this case, if you take for the rectangle, the horizontal line which is passing through the bottom of the object is treated as x-axis. Y-axis is representing vertical line passing through the extreme left. In this case, the position of the centroid gravity is represented as coordinate to the half B. Similarly, and height is equal to half of its height now. That is nothing but here it can be represented at the center like that. Similarly, for the triangle now, the center of gravity always lies at a distance of 1/3 of its height from its base position. For the circle, since the object is symmetrically for x-axis and y-axis, the intersection of x-axis and y-axis, that is treated as here the origin. Here it is also called center of circle. That is represented as center of gravity. Hence, x-coordinate and y-coordinate both are treated as 0. For semicircle, the area is half of pi r square. Again, the object is symmetrical about the vertical and horizontal axis. So here, the center of gravity lies at a distance of 4r by 3 pi, lies on vertical axis. That is the x coordinate is treated as 0 now. Similarly, for the quarter circle, the position of centroid lies on a symmetrical line, that is which is making an angle of 45 degrees, and it is at a distance of x-axis and y-axis 4r by 3 pi now. For the ellipse, the area is equal to pi AB. Since the object is symmetrical about the horizontal axis and vertical axis, the intersection of this axis is treated as origin. So origin is treated as the position of center of gravity or the centroid. The second one is by using method of moments. Here, according to this procedure, the object is assumed to be divided into number of segments. If it capital M is representing the mass of the object, and M1, M2, M3 and so on Mn are representing the elements which are divided, let the first element M1 is at a distance of x1, y1 from the reference lines x-axis and y-axis as shown in figure. Similarly, x2, y2 for M2 elements, and M3 again x3, x4 and so on. Let xc and yc is representing the position of center of gravity with respect to the reference lines. So, according to the principle of moments, that is the moments created by all the elements at one point should be equal to the moments created by its entire object now. So, according to the principle of moments, m into xc, or we can take this, if it is the weight is there now, that is the moment created by the resultant force. Resultant force means here the entire weight of the object is equal to the moments created by the elements weights at that reference line now. That is here m into g, that is the weight now, into xc is equal to m1g into x1, m2g into x2 and m3g into x3 and so on. Since g is the constant now, it can be written as now mxc is equal to m1x1 plus m2x2 plus m3x3. This is nothing but with respect to the y-axis. Hence, xc is equal to sigma of mx divided by m now, where m is equal to m1 plus m2 plus m3 and so on. Similarly, the position of centroid with respect to the x-axis is given by yc. It is equal to sigma my divided by m now. Centroid for the two-dimensional objects. Here, the two-dimensional object, when you are taking, the thickness of the object is negligible, or sometimes it is also having this uniform thickness now. Hence, here the mass can be written as now, that is the m1, it is equal to, we can take it as, that is the area 1 into thickness, we can take it now. That is the uniform thickness we are taking. Hence, according to the previous relations now, xc is equal to sigma mx divided by sigma m, that is the total mass. It can be written as simply m1x1 plus m2x2 plus m3x3 divided by m, which is equal to here now rho into t into a1, that is nothing but mass now, into x1 plus rho into t into a2 x2 plus rho into t into a3 x3 divided by rho t a now, where rho stands for the density of the materials, that is the mass per unit volume, and t is representing uniform thickness, a1 is representing the area of the each elements now, one first element, second element, third element, like that. So, on simplifications we got it is equal to sigma ax divided by a, since rho and t both are present in denominator and numerator, get cancelled now. The remaining is sigma ax divided by a. Similarly, yc is equal to sigma ay divided by a now, where a stands for the area of the entire elements, which is equal to the sum of a1 plus a2 plus a3 now. Now centroid for the one-dimensional body. Here one-dimensional is treated as the wire which is having uniform cross-section now. So the mass of the element here M1 first element, it can be written as now length into area, and first length nothing but area of the cross section is uniform, which is in the form of wire we are taking, into T we can take it now. That is the density of the material, so we can take it as rho now. So L1 A into rho we can take it now. That means here XC is equal to, according to the relations now, M1 x1 plus M2 x2 plus M3 x3 divided by M. It can be written as now rho A L1 x1, because the area of the cross section is remains constant because we are taking it is in the form of uniform wire, that is the one directional object. Rho T A L2 x2, rho T A L3 x3 and so on divided by rho L A now. Since rho and T both are constant now, the remaining values is rho A both are constant, which are get cancelled because which are present in both in denominator and numerator. The remaining values is equal to L1 x1 plus L2 x2 plus L3 x divided by L, where L stand for the sum of the lengths of all the elements. Similarly, Yc is equal to sigma Ly divided by L now. Okay, center of gravity of symmetrical section now. Here symmetrical sections means it may be aleator, it may be the rectangle or the circle. The intersection of the reference lines, when it is a symmetrical means here now, it is in the form of here rectangle. The symmetrical means here vertical line as well as the horizontal lines we drawn. The intersection of these two vertical reference lines meeting at a point O, that is treated as position of center of gravity now. This is applicable for all symmetrical lines, symmetrical objects. The symmetrical objects means sometimes it may be symmetrical about the x-axis as well as the y-axis. Sometimes it may be the symmetrical with respect to the only one axis now. Example here I am taking now, the T section it is there. This object is symmetrical about the vertical line now, that is the y-axis now. The lowest position is treated as the x-axis and y-axis. In this case, since the object is symmetrical about the vertical lines, the center of gravity of the object lies on vertical lines, that is the x coordinate is equal to 0 now. Hence, we have to determine only y coordinate to represent the position of center of gravity or the centroid now. Hence, if we identify the symmetrical lines, the location of the centroid or center of gravity of the object becoming simple now. Center of gravity of unsymmetrical sections. Some sections are there now which are not at all symmetrical about the vertical lines and horizontal lines. In that case, the horizontal line which is passing through the lowest portion of the figure or the object is treated as the x-axis, and the vertical line which is passing through the extreme left of the object is treated as the y-axis. With respect to the x-axis and the y-axis, we have to determine the position of the centroid or the center of gravity of the objects. This is the way of representation of reference lines for the symmetrical as well as the unsymmetrical sections. Here I am example taking the composite section. It is there. It is in the form of T section now. On observing this object is symmetrical about the vertical lines. Hence, it is treated as the y-axis now. The bottom of the lines, this is treated as the x-axis. Since it is symmetrical about the vertical lines, the determination of central x coordinate of the center of gravity is not required because it lies always on vertical line only. Then the y coordinate is obtained after dividing the T section into some regular segments. The regular segments, it may be in the form of maybe the square, or it may be the rectangle, or it may be the circle, or the triangle, or semicircle, quarter circle, and so on. But here, it is possible only to divide the object into two segments, two rectangles now, which are already represented here now, A, B, C, D, as well as the E, F, G, D. So, in this case, the procedure for determining the center of gravity is only y coordinate required. Hence, yc is equal to, we can take it as a1 y1 plus a2 y2 divided by a1 plus a2 now. Here, for this object now, here it is in the form of, here L section it is there. We divided the segment into two parts now, 1 and 2. On observing this object, it is not at all symmetrical about the vertical line or horizontal lines. In this case, the way of representing the reference lines are the line which is passing through the extreme bottom of the figure, it is treated as a x-axis now. Extreme left, it is treated as a y-axis and so on. Afterwards, divide the given object into regular sections now, regular segments. That is, it is in the form of rectangle, square, triangle, circle, semicircle, and so on now. Here it is possible, according to the figure, we can divide into two parts. That is, two rectangles are there now. It is represented here 1 and 2 now. Now, by using the relations now, xc is equal to a1 x1 plus a2 x2 divided by a1 plus a2. Similarly, yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2 now. Where a1 is representing the position of the area of the first rectangle, a2 is representing area of the second rectangle, and x1 is representing position of centroid of the first triangle with respect to the y-axis. x2 is representing position of the centroid of the second rectangle with respect to the y-axis. Similarly, y1 is representing the position of the centroid with respect to the x-axis of first rectangle. y2 is representing position of the centroid with respect to the y-axis now. So, after determining x1, y1, x2, y2 and areas a1 and a2, by using the relations xc is equal to a1 x1 plus a2 x2 divided by a1 plus a2. Similarly, yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2. We can determine the position of the centroid. Already, just I told, the center of gravity, it is only related to the solid objects which are having weight now. They are such as hemisphere, cylinders, right circulars, solid cones, and so on. Since if the object is made up of same materials now, that is, if it is not at all composite objects, in terms of volumes, we can determine the position of the center of gravity. Okay, the object is, if it is a composite figure, it can be divided in the form of rectangular objects, or cylindrical objects, or hemisphere, or right circular solid cone, and so on. Here, the area of the volume of the bodies are volume of the cylinder is equal to pi r square h. Volume of the hemisphere is equal to 2 by 3 pi r cube. Volume of the right circular solid is equal to 1 by 3rd pi r square h now. So after knowing, depending on the position of composite object, we can write as xc is equal to, we can take it as m1 x1 plus m2 x2 divided by m1 plus m2. If it is made up of same material, that object is same material, it can be modified as v1 x1 plus v2 x2 divided by v1 plus v2. Similarly, yc is equal to m1 y1 plus m2 y2 divided by m1 plus m2. If the density is constant, the modified equation is v1 y1 plus v2 y2 divided by v1 plus v2, we can write it. So by using the relations, we can determine the center of gravity of the solid objects. Moment of inertia, radius of gyration, polar moment of inertia, and theorem of moment of inertia. Okay, moment of force now. Generally, moment of force can be determined with respect to certain point. That is, with respect to the reference point, we can determine the moment of a force. It is the product of force and perpendicular distance between the point and line of action of the force. If P is representing the force that is acting, here now, assume this is nothing but a force is acting, P. Here it is our reference point, O is there. If the perpendicular distance between the line of action of the force and the reference point, if it is x, the moment of force is given by the product of force and the distance, which is equal to P into x. This moment is also called first moment of a force now. If this moment of force is again multiplied by the distance second time, that is px into x px square, this quantity is called moment of inertia, simply written as moment of inertia, simply written as m into I now. Here we have taken the moment, that is the force is multiplied by the square of the distance. If it's single time, when we multiply, we use the words, it is the first moment of force. When we multiply that area second time also, it is called second moment of force. Simply it is called moment of inertia. But this same word, it is also applicable when the area is multiplied by the square of the distance. Similarly, mass is also multiplied by the square of the distance. It is the terms, generally it is as second moment of area, second moment of mass, or simply it is also called moment of inertia. Here moment of inertia means the force, mass or the area, it is multiplied by the square of the distance which lies between the reference point to the point at which the force is acting or at which the area is concentrating. The moment of inertia of a plane area. Here, assume this object is now, it is divided into some number of segments, A1, A2, A3 and so on now. Now each segment is here represented with the coordinates now, x-axis and y-axis, and x1, y1 is representing the center of gravity of the first mass, first element. Similarly, x2, y2, second element and so on now. R1, R2, R3, they are representing the position of the center of gravity of each element from the reference lines. The moment of inertia, it can be represented as about the y-axis nothing but it can be represented as it is equal to I-axis, I, y, y is equal to we can take it as a mass, that is the m1 into x square plus m2 x square plus m3 x square and so on. Similarly, about the x-axis is equal to m1 y1 square plus m2 y2 square and so on. If R1 is representing the position of central gravity with respect to certain reference line, then the moment of inertia of that area, it can be represented as A1 R1 square plus A2 R2 square plus A3 R3 square and so on, which is equal to sigma of area AR square now. Now from this relation now, we are discussing moment of inertia of a plane area only. Hence, the area units of mm square now, radius also, if it is represented in mm square, that is nothing but if all the dimensions are represented in millimeter, then the units of moment of inertia are represented as mm to the power of 4 now. If they are represented in meters, the moment of inertia is equal to m to the power of 4 now. Methods for determination of moment of inertia. So, here the moment of inertia of plane area of the objects can be determined by following two methods. The first method is Raoult's rules. The second method is by the integration. According to the Raoult's rule, state that the body is symmetrical about the three mutual perpendicular axes. Then the moment of inertia about any one axis passing through its center of gravity is given by I is equal to ARM into S by 3 now. Here, if a body is symmetrical about the three mutual perpendicular axes, then the moment of inertia about any one of the axes passing through its center of gravity can be determined by using the equations ARM into S by 3, where A stands for the area of the plane figure, or M stands for the mass of the figure, multiplied by S by 3 now, where S is nothing but representing the square or rectangular line. This is nothing but applicable for the square or rectangular lamina, where S is equal to sum of the squares of two semi-axes other than the axis on which we are measuring moment of inertia. Similarly, ARM into S by 4, this 4 denominator, when it is coming, it is applicable for circular elliptical lamina. ARM S by 5, it is for spherical body now. That is based on the denominator values now. ARM into S by 3, square or rectangle, S by 4, circular or elliptical, 5 spherical bodies now. Where A stands for the area of the plane area, M is the mass of the body, and S is equal to sum of the squares of the two semi-axes other than the axis about which the moment of inertia is required to be determined. Hence, this Raoult's rule is having limited applications. It is only applicable for the determination of moment of inertia of the objects or the plane areas which should be symmetrical about the three mutual perpendicular axes. Hence, it is having its limited applications in determination of moment of inertia. The second one is moment of inertia by the integration now. Here the object is kept just in a coordinate planes, that is the x-axis and y-axis as shown in figure. Let xy is representing the position of its centroid with respect to the coordinates axis. The moment of inertia about the y-axis is given by sigma of dA x square, and about the x-axis is given by sigma of dA y square now, where sigma dA is representing the area, entire area of the given object now. Here the same object again we are considering now. dA is representing the area of the small element having its coordinates x and y with respect to the y-axis and x-axis as shown in figure. Then the moment of inertia of this elementary object about the y-axis is given by Iyy is equal to sigma equal to dA into x square now. That entire object is given by sigma of dA x square now. Similarly, Ix is equal to sigma of dA y square now. If R is representing the position of the element with respect to the origin of the coordinate axis, that is the intersection of x-axis and y-axis, then the line which is passing through the origin and perpendicular to the plane is called z-axis now. Izz is equal to given by, here we can write it now, Izz is equal to, we can write it sigma of dA into r square now. But according to the geometrical conceptions, it can be written as now sigma dA into r square is equal to x square plus y square, or sigma dA x square plus sigma dA y square now. This is equal to Izz, or nothing but the moment of inertia about an axis which is perpendicular to the plane, that is Iz, about an axis which is perpendicular plane, that is Izz, it is equal to the moment of inertia of the same object about the two perpendicular axes passing through a point 1 now. That is sigma dA x square plus sigma dA y square now. This theorem is called, that is Izz is equal to Ix plus Iyy is called perpendicular axis theorem. Similarly, the moment of inertia about the parallel axis is given by the moment of inertia about an axis in the plane area is equal to the moment of inertia about a parallel central axis and the product of area and the square of the distance between the two parallel axes. This theorem is known as parallax theorem. According to the parallax theorem, the moment of inertia of an object about any axis means according to this figure, it is equal to AB is equal to the sum of the moment of inertia of that object about its central axis, which is parallel to the AB, that is the given line, and the product of area multiplied by the square of the distance between these two parallel lines now. That is IAB is equal to IGG plus AYC square now, where IAB is representing the moment of inertia of a plane area about a line AB. IGG is representing moment of inertia of the entire object about its central axis, which is parallel to AB. A is representing area of the object. YC is representing the distance between the two parallel lines, that is GG and AB now. Polar moment of inertia. The moment of inertia about an axis perpendicular to the plane of an area is known as polar moment of inertia. Generally, it is represented as JRIZZ. According to the geometric construction now, Ix is representing the moment of inertia about the x-axis. It is equal to sigma of dA y square. Similarly, Iyy is equal to sigma of dA x square, and Izz is equal to, Izz means nothing but the axis which is perpendicular to the plane and passing through the intersection of x-axis and y-axis, that is the O point. This is treated as z-axis. Izz is equal to sigma into dA into r square, or sigma into dA r square is equal to x square plus y square, we can take it. R it is equal to ix plus iyy. That is the polar moment of inertia. It is equal to the sum of the moment of inertia about the two perpendicular axes which lies in the plane of the area, that is ix plus iyy. The radius of gyrations. Mathematically, the radius of gyrations it can be represented as k, which is equal to under root of I into a, or I is equal to a into k square, where I is representing the moment of inertia about an axis, a is representing the area of the element, and k is representing the perpendicular distance between the axis as well as the given the plane area. From these relations, we can determine k is nothing but radius of curvation. It is the distance between the center of gravity of the object to the axis, which is squared and multiplied by the area. Just it gives the moment of inertia about that axis now. The moment of inertia of some simple sections now. For the rectangle, about the x-axis is equal to ix is equal to bh cube by 12. Radius of derivation is equal to h by under root of 12 now. For the triangle, about the x-axis is given by bh cube by 36. For the circle, pi r square by pi r to the power of 4 divided by 4 now. And for the semicircle, 0.11 r to the power of 4. For the quarter circle, ix and iy both are same, which is equal to 0.055 r to the power of 4. For the ellipse, ix is equal to pi a b cube divided by 4. Iyy is equal to pi b a cube divided by 4 now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.